Hello everyone, we are from Section 1, Group 7. Today I'm going to demonstrate our project part 2, which is optimizing image filters with high-level synthesis. Our group consists of 4 members: Brian Chong Ting On, Chong Wen Yang, Dixon Chong Yong Hao, and Tang Junling. After that, let's look at the optimization approaches for both best performance and best energy design. Here's the C++ code in Vitis. The first optimization is changing the data type for input and output array by changing it to unsigned character, which is unsigned 8-bit. After that, we do array partitioning for the input array by using dimension equal to 2, vector equal to 4, and using the cyclic type. Then we do loop unrolling for the second most outer loop with vector of 8. And then we use pipeline and loop unrolling with vector of 2 for 2 of the inner loop. Then we'll look at the result of the optimized design. First, we'll run a C simulation first to verify the optimized design. As you can see here, the output log file shows that the design has passed simulation. Then we'll do C synthesis to see the estimated performance of this design. As you can see here, the estimated time is 5.671 nanosecond, and here are the estimated latency and also resources. Next, we are going to run a core simulation to verify the post-synthesis design. After a core simulation, then we can see the control signal here. After we complete core simulation, now we have to put the Verilog code into Vivado to see a more accurate performance results. First, we are going to apply a timing constraint of 10 nanosecond clock into the design, and then we will run synthesis and also implementation. After synthesis and implementation are done, we can look at the results in project summary. First, we're looking into timing performance. As we can see, all of the slacks are positive, means that there is no timing violation in this design. After that, we're going to look into the resource utilization. As you can see, most of the resource used are I/O port. You can see in this table, there are a total of 1,468 resources have been used. After that, we'll look into the power performance. As you can see, there's a 0.241 watts of dynamic power and also 0.452 watts of powers. The total power used is 0.693 watts. Next, we're going to look at the optimization approaches for best resources. This is the C++ code in Vitis for the best resource design. Similarly, the first optimization is data type optimization by changing the input and output to unsigned 8-bit. Next, we're going to use HLS allocation directive to limit the multipliers into 2. Next, we are also do loop unloading with a factor of 2 for the most inner loop. Then we'll look into the result of this design. First, we're going to do C simulation. After simulation had done, we can clearly see that the design has passed the simulation. After that, we will run C synthesis. After C synthesis have done, we can see the estimated time and also performance and resources. The estimated time is 4.622 nanosecond. Then you can see the latency and resource usage in the performance and resource estimates. Now we're going to run a core simulation to verify the post-synthesis design. After core simulation had done, we can see the control signal in this waveform. After that, we're going to import the Verilog code of the design into Vivado. As you can see here, there are also 4 low-level blocks which are 2 multiplexer and 2 multiplier. Similarly, we also give a constraint of 10 nanosecond clock for this design before we run synthesis and also implementation. After synthesis and implementation have been complete, then we can see the results for this design. First, we are going to look at the timing performance. As you can see here, all of the select are positive, which means that this design is free from any timing violation. After that, we are going to look at the resource utilization. As you can see, most of the resource used are I/O resource, which it occupies 32% of the I/O port in the FPGA. After that, we can click on the table. You can see the total resource usage is 387. Next, we're going to look at the power performance. The dynamic power is 0.043 watts, while the static power is 0.451 watts. It results in a total power of 0.494 watts. Alright, that's all for this demonstration. Thank you.